Welcome everyone. For today's prep, we're going to start a new differentiation technique called implicit differentiation. And before we get into the process here, we have to first look at, well, what type of function are we going to be considering here? And in general, there's two types of functions. And all the functions we've been looking at so far are what we would consider explicitly defined functions. So these are functions where there's a clear process. You take your input x, you plug it into the machine, and the steps are all laid out for you, and you can get output y. So an explicit function, this is really what we're most familiar with, but an explicit function is written in the form y equals f of x. All right, so we've seen how to differentiate these types of things. We've learned some whole bunch of derivative rules now. What we're going to be looking at today, though, is kind of a new grouping, new class of functions called implicitly defined functions. And these are types of functions where there's not a clear set of steps to follow in order to take your input x and get output y. So you kind of have to do more work. And the difference here is these are not written in the form y equals f of x. Okay, so two examples. The first example, this is this parabola here. This is what we would consider kind of a usual thing. This graph is explicitly defining a function. And the formula for this one is y equals x squared minus 1. So when we take input x, there's a clear set of steps I can follow to get what the output y is. So I can square my x term, and then I can subtract 1, and then bingo, I have my output y. So there's a clear set of steps I can follow in this formula in order to start with my input, get my output. Now in this other graph we can use to implicitly define a function. Now what's the equation for this graph? Well, the equation is x squared plus y squared equal to 4. And there's not a clear set of steps that this formula lays out for me that if I take input x, I can immediately get input y, or output y. I have to do more work in order to then solve the equation and figure out what y is equal to. All right, but in either case, so what we're going to be looking at today is how do we differentiate, how do we calculate the derivative when we have an equation like this, where it's not in the form y equals. And the derivative in either of these cases, dy dx, well, our interpretation of the derivative in the explicit case, this is what we've been working with all along, this is the slope of the tangent line. At point P. So if we have a point that we're interested in, we can use our derivative to get the slope of the tangent line at that point. And once we have the derivative in this implicit case, well, the derivative is still going to have the same interpretation. It's giving us the slope of the tangent line. So if we have an equation like this, how do we calculate the derivative? And we're going to be starting with an equation that has two variables, normally x and y, but doesn't have to be x and y. And in this case, in the problems we're going to be looking at, we're going to view y implicitly as a function of x. So that's what we're going to be doing. We're going to be treating y as, in our equation, we're going to be treating y as kind of secretly defining a function of x. All right, so when we have an equation with x's and y's in it, what we're going to do is we're going to treat, well, each of them like a regular variable. So it's an equation. We're going to treat each of them like a regular variable, but we're also treating y as something extra. So we're also going to treat y as a function of x. So that means when we have an equation and there's a term that only has an x, because we're treating x just like a variable, we're just going to differentiate that term like regular. Now for y term, we're treating it first of all like a variable. So when we go to differentiate a term that only has a y in it, we're going to differentiate that like usual. But because we're also treating it as a function of x, you can almost think of it like there's a whole bunch of little x terms hidden inside the y there. Because we're also treating it as a function of x, we're then going to multiply that result by y prime. So let's try an example to see how we're going to be doing this. So let's look at that equation, x squared plus y squared equal to 4. And we're going to use the technique of implicit differentiation to calculate the derivative dy dx. All right, so the first step, let's write our equation. X squared plus y squared equal to 4. And our first step is to go through that equation and for each individual term, apply the derivative. So we're going to apply the derivative to the x squared. And actually, helps to kind of space things out a bit. You don't want to be all cramped when you're writing things. So give yourself enough room. All right, so we got our x squared plus y squared equal to 4. And now we're going through and we're applying the derivative to each one of these terms. Okay. So let's look at this first term. That's an x squared. There's only x's in there. So we're just going to differentiate that like regular. So derivative of x squared, if we do our power rule, 2x. All right. So now we go on to the next term. We got y squared. So we're going to, first of all, we're going to treat y like a variable. So we're going to differentiate that just like regular. So we get 2y. Okay. But because this is a y term, we're then going to multiply that result by y prime. Or if you want to use dy dx here, you can. That's fine. So notice for this y term, there's a little bit extra. We differentiate like regular, and then we multiply by y prime. And then we go on to the other side of our equation, and the derivative of that constant, just 0. So nothing too crazy there. All right, so once we get to this equation, now we want to solve for y prime. And the way we're going to do this is we're going to get all the terms with y prime on the left-hand side of our equation, and all the terms that don't have y prime, we're going to move to the other side of our equation. So this 2x, we're going to move it over. And the way we move terms around when there's addition involved is with subtraction. So we're going to subtract 2x from both sides. So if we do that, we get 2y times y prime is equal to negative 2x. And then we want to solve for y prime. We have all this extra stuff that's attached to it, this 2 times y. So how do we get rid of this? We want to move it to the other side, but this stuff is attached by multiplication. So how do we undo multiplication? Well, we divide. So we're going to divide both sides by that 2y. So we end up with negative 2x over 2y. And that's our derivative. If we simplify it, we get dy dx is equal to negative x over y. And when we do implicit differentiation, this process that we just did is called implicit differentiation. When we get the derivative, it's going to look a little unusual than what we're used to, because there's a lot of times there's going to be x's and y's in our answer here, and that's fine, because we didn't start with an equation that was y equals this. Here the x's and y's were all kind of mixed together, so when we do our derivative, we end up with a derivative where the x's and y's are all mixed together. So that's fine. And while we're at it, let's do the second part. So now that we have our derivative, we can play all of our usual games with the derivative. So one of the things we've looked at is finding the slope of the tangent line, or the slope of the graph. So how do we get the slope of our tangent line? Well, so to get the slope at the point 1 comma square root 3, we're going to take our derivative, dy dx, and we're going to evaluate it. Now, our derivative have x's and y's in it, so when we go to evaluate, we're going to have to use both the x and the y value from our point. So the x coordinate is 1, and the y coordinate is square root 3. So we're going to plug x coordinate in for 1, and y coordinate is going to be square root 3. All right, and this big line just means evaluate. So we're going to take the derivative, we're going to evaluate, and we're going to plug our x coordinate in, which is 1, and then our y coordinate in, which is square root 3. All right, so let's get our formula here, negative x over y. We're going to evaluate. And when we plug in, our x coordinate is 1, so we'll plug that in for the x. So we get negative 1, and then our y coordinate is square root 3. So there's our slope. All right, so that's the idea. And in class, we'll talk a little bit more about why we're multiplying by this y prime. It comes down to chain rule. So we have to see chain rule first, but it essentially we're multiplying by the inner function here. And some of the later examples we'll see, well, what happens if you have a term that is not just a single x or a single y like this? What if you have terms that have both x's and y's? And in that case, depending on what you have, you might have to use one of those more advanced derivative rules, product rule, quotient rule, or chain rule. So we'll get a little practice with that in class. So we'll see you then. Bye-bye.